In the last video, we put together a wavetable oscillator with a few tweakable parameters. Now it's time to build a module that can automatically tweak those parameters. Usually this is called an LFO, or low frequency oscillator, just a signal that goes up and down once every second or so, as opposed to audio signal, which is at least 40 times a second or more. In the style of modular that I do, I pretty much only use a very specific type of LFO, which instead of syncing up to a sine wave or a specific frequency or waveform or something, it just sort of meanders around randomly. So that's what I'm going to build. The abstract way to model this would be to take a random noise source, run it through a sample and hold with a specific clock pulse, and then slew the output of that. But instead of using 4 different modules to achieve this effect, I might as well just shove all of that functionality together into a single box. The heart of our module today is the SAMD21 microcontroller, which is an ARM Cortex M0 chip, the smallest ARM chip you can get. The biggest constraint here is that we're living in integer land. While we can use floating point numbers, there's no floating point instruction set in the M0, so any operations that we do would be on the software level, which is just going to be way too slow for real-time audio. The rest of our breadboard is pretty simple. We have an output jack, and a jack and a knob for our one tunable parameter, which will control the speed of the meandering from a lazy stream to some kind of water that moves really fast, a fire hydrant, I guess. The wiring diagram here is also pretty simple, just connecting all of the grounds and a 3.3 volt to the potentiometer. Then each different data wire goes to a different analog pin on our microcontroller. Part of me thinks I should put like a resistor or a diode somewhere. I look at these circuit diagrams with like 1,000 different capacitors and I feel like I'm doing something wrong. Are weird capacitor placements just job security for electrical engineers? With that done, we can now escape back to software, where I can much more easily pretend that I know what I'm talking about. To start off, we have to go off into signal processing land for a bit. For all the fancy software out there for modeling and doing whatever, the best tool for signal processing for me will always just be a spreadsheet. The workflow generally goes, start with one column with your input data, then each successive column you add in a filter operation. You can use different charts to see how you're doing. After filling up hundreds of thousands of little boxes with numbers and forgetting why you wanted to do this even in the first place, you start looking for a different career path. You like trees, maybe something outside like the Forestry Service. Then, halfway through your application to the National Park System, you start to think about those squiggly lines again. An idea for a finite impulse response filter hits you like a brick. You solve your problem. The squiggly lines look exactly how you want them to look. They're perfect. It's just another day in the office. Anyways, our starting signal is a random 16-bit value. We're using a tiny little chip, and we don't need to secure Bitcoin with this random output or anything, so we can keep it simple here by just doing a successive add, then multiply, then modulo, or take the remainder of some prime numbers. I'm too far removed from my number theory classes to remember which one of these need to be prime and why they need to be prime, so I'm just going to make them all prime. I'll leave the proof to why this works to the one person listening who has Maple installed. It's important here to try a bunch of different numbers aimlessly until the graph looks how you think random numbers should look. Those other ones weren't really random, but yeah, that's random. The numbers we generate here will loop back to the beginning every 65,000 samples. This is usually the main downside to using a random number generator in 16 bits like this, but it actually turns out to be a huge positive for us because we only need to check 65,000 values to make sure that we don't have any outliers or weird stuff going on. After getting all that sorted out, I spent like 4 hours trying to come up with some fancy sigmoid balancing function that would be all smooth and nice, until I remembered about the earlier constraint of we're just using integers, and the negative real numbered exponentation is probably a bit of an expensive operation for us. So instead, we're just going to do a bunch of moving averages. Everything in signal processing can be fixed by moving averages. Here we chain together 3 of them to really smooth things out until it looks like how I think it should look like. The big trick of this process is to have a very rough idea for what you want, and then just aimlessly change around numbers until the graph looks sort of good enough to convince yourself that you can stop. Then you can give up and go drink some off-brand soda. I don't know, it all just tastes the same to me. Okay, now that we have equations that we like, we can move them over to Python code. The main things to note here is that we have an infinite loop, and then we're setting previous values over and over again. I assume this is how everyone does this sort of thing, but thinking about it now, I've never actually checked, so now I'm kind of self-conscious, so I don't know, this works. Other than that, it's just some pretty simple mapping from our Excel equations into Python code. Alright, so we've successfully done the whole random meandering thing, but we still need to control the speed at which it randoms around. To achieve this, I want to use something called interpolation. Basically, our speed knob will decide how many samples we spend going from one of our randomly generated values to the next. Okay, now let's test this out and see if we're in the right ballpark. Good enough. Now I can move everything out to the perf board. It's exciting, I actually got perf board to move the circuit to instead of the wild breadboard thing that I was doing before. There's definitely a learning curve to making the wires neat and all of that, but I feel like I'm doing a good enough job of being budget bin eater. I've found that soldering really rewards patience. If you let the joints cool down a bit, they're way easier to connect, and too much heat just makes a big mess. Unfortunately, I learned that while soldering this board, so this one's a bit of a disaster. But as long as the electrons can go where they're supposed to go, I guess it's fine. So the other day I was talking to my friend, who's a mechanical engineer, about the best way to make the cuts to these enclosure boxes, because this is not really what I know how to do. And so I learned that I'm definitely doing it wrong, like very wrong, but it still works, and I don't want to buy more tools, and so we're just gonna keep doing it this way, and I'm not gonna worry about it, and it's fine. And with that out of the way, we can take a second and paint the module. This is the time where you can take a breath and think about the aesthetics of all of this. When I show someone this module, they aren't going to recognize how clean my RNG algorithm is, or how well thought out the interpolation system. They'll probably just say, "Nice. It's purple. That's a good color." And they'll be right. Purple is a good color. At the end of the day, it doesn't matter so much how we got to the goal, just that the thing does what we want it to, and it sounds good, it looks good, and it makes me feel good. Put together the last few little bits, and there we go. That is definitely a module. Let's see how it sounds. And there we go. Thanks for joining me on this process, and I'm happy with how it turned out. I'll see you for the next one. Bye.